Hey, what's up?
Not much. How are you?
Yeah, it's going.
You right? I'm gonna keep my camera off because I'm eating lunch. I'm a bad student.
Oh, oh man. Sorry, I have this simultaneously streaming to YouTube.
Oh, cool.
So it the first time you do it in a specific room, then you have to sign in and do all that stuff.
Oh, no problem. How's it going?
It's going, it's a weird semester, but we're here. We're doing it.
Right.
Yeah.
Lots of fun.
How are you doing?
Good. I mean, it's ever since we've been home, I don't think I've ever been as busy. And so that's kind of crazy. And then I'm starting all of these drop-ins for the new people. And so I have like a lot of them.
Sure.
So I'm kind of doing that. And then so it's just hectic, but you know what? I like it. I really like my job. So that's good.
Good. That's good.
My kids are finally back in the classroom. I like that.
Yeah, my wife is starting to get some of her students back some of her students back now too. They're doing the younger grades first in Chandler, and then she'll get her students not next week but the week after come back in the classroom. But she felt like she was just hitting her groove with like the whole Google Classroom and stuff, and then they're gonna switch it back now. So
Yeah.
kind of like mixed on it.
It's just one of those things where you just kind of have to roll with it. And if you don't have the personality to roll with it, you might as well just quit. It's like we
Yeah.
literally my kids and I were talking about their last day at school and my last day at work, where you were just like, hey, why don't you stay home for a while? And then we've never gone back. It's just bizarre.
Yeah, it is. It's surreal too being on campus right now because it's so few people. So it's like
I know. And when I would go out when this all started and I would go to the grocery store, I would take pictures of like the empty shelves and show them to my kids to be like, this is what's going on out there. But they were, I mean, they were chomping at the bit to go back.
yeah, it's a thing, certainly a thing, right?
One of my daughters was like, don't take this personally, but I've really had it with you all. Like, listen, preaching to the choir,
Like,
girlfriend.
that doesn't stop at kids, right? Like doesn't just apply to you guys.
No, yeah, yeah. All right, you do your thing.
All right, cool.
I'm just gonna be here.
Wait, just waiting for the class to show up.
Yeah.
By the way, thank you again for doing it. Appreciate it.
Oh my gosh, my pleasure. Totally, my pleasure.
Hey Alexis, how's it going? I'll be back in 1 sec. You guys have a good weekend? Maybe, maybe not.
I did, yeah.
Yeah.
How do you guys feel after the first week is completely done of being online, right? How do you guys feeling? Feeling all right?
It's not as bad as I thought it was going to be. So,
I have a feeling that's going to be a motto for the whole semester. Fall 2020. It's not as bad as I thought it would be. Hey, Brandon.
Hello there.
Hey, what's going on?
I actually rested and I feel kind of decent now.
Oh man, nice.
It's very surprising.
It's amazing, right? If you actually go to sleep and
Well,
sleep for and rest, right? Like your body starts to feel better. It's crazy.
it really is. This morning I was like basically dying. I think the professor thought I was winking at them constantly because my eyes were just going like up, down, just trying to stay awake.
Man,
Ugh.
yeah.
I've definitely been there. Not proud of it, but
Very
yes, I know exactly what you mean.
Yeah. I'm glad you understand.
All right, so it's 12:30. I'm sure everybody else will kind of roll in a minute, but we're gonna get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you've done for us and all that you continue to do. I pray that you would just continue to keep us focused even though we're online. Help us get through the rough patches of this semester and just be focused and continue to exert the effort that we need to. In your name we pray. Amen. All right. So what are we doing today? Right? Let's see. So we're going to talk a little bit today. Well, first, this is I'm prepared for this though. This is obviously it's not showing you what it needs to show you, but this should right here, right? So can you guys see the poll everywhere now as I put it up there, right? Is it all right? Is everybody able to see it? The plugin wasn't working, so I'm hoping you can see this, right? So integration formulas were the biggest things that people were having issues with, right? And I mean, we did a good review of integration on the first day. It seems from talking with some of you that symbolic integration is, and symbolic math in general is what's kind of the stumbling block right now. And it's not always necessary to do it that way, but I do think it is best practice to do everything symbolically until the end, and then you can just you just plug in your numbers, right? The reason that I would say that is because, say, for example, you're doing the homework, right, on McGraw-Hill, and you get it wrong 3 times. So you have to submit a second attempt, right? And so you have to, and you get different numbers now, right? How are you going to, are you going to want to redo your entire work because you did it all the way through with numbers, or do you want to just do the last few seconds where you plug in some numbers, right? So that's why I say that to you guys. Is it necessary for you to do it that way? No, but it is really helpful in the long run. And it does seem like it takes more time up front. But as my PhD advisor always said, you should do a lot of work up front so you can be lazy at the end. Okay. Let's see, formulas. There are formulas, right? We're talking about kinematic equations. I apologize, I didn't put those up on LoudCloud. I will post them today right after class. I'm writing a note to myself, post kinematic equation sheets, right? Those are going to be really helpful, right? We'll see why today. We'll see why today when we go through some of these problems, right? Especially in projectile motion. Other than that, it looks, basically like some iteration of formulas or integration, the problems, right? So let me ask you guys this. Do you have any other major issues that you'd like for me to go over before we start going into the other stuff for class today? Everybody's feeling okay? And remember, I know you guys all did the Learn Smart, so that's good. We've got a homework and another couple of Learn Smarts to do this Sunday, right? So make sure we do that. Nothing else? Everybody's all right? Once, twice? Okay. All right, so let me ask you guys this, right? So this weekend I was hanging a painting in my bathroom. I fell off the toilet that I was standing on and I hit my head on the sink, right? So I'm a little bit fuzzy. So what did we do? What did we do last week? Can you guys name 3 things that we did in class last week? Don't be shy, just unmute and shout them out.
We came up with team names and flags.
Okay, sure. I was hoping we would like focus on some other stuff that like was like, content relevant, but sure, we did do team names and flags. I'll count it. I'll count it this time.
Like the integrations of for acceleration when it's in relation of time or velocity.
Sure. So say integration, right? What's one other thing?
Derivatives and integrals given equations. So like how to find velocity and acceleration based off the position equation.
Exactly. And both of these things, right, that you guys are describing is generating kinematic equations, right? And we actually went over the specific case. Well, what happens when I have a constant or a uniform acceleration, right? That was one of the cases that we went over. And when we do that, it simplifies our equations really nicely and neatly. And we get these equations that you guys probably saw in Physics 1 that we use quite a bit. And those are the kinematic equations for uniform acceleration, which I will post on LoudCloud right after class so that you guys can have them to do your homework and whatnot, right? All right. You guys have any major issues, questions, concerns so far? Everybody feeling okay before we move on? Looking. Seems like everybody's okay. Okay. Cool. Bonus points, right? Well, there's no points associated with this, but bonus points. What did I, right? If this statement was true, who would I be? It's a movie character. Can you guys name the movie character who fell off his toilet while hanging a painting and hit his head on the sink? No. It's Doc Brown from Back to the Future. That's how we invented the flux capacitor. If you haven't seen Back to the Future, then your parents have failed you, and you should go check it out. Okay, so here's the things that are due. If you haven't done the lab safety waiver, please do the lab safety waiver, right? After this week, that's gonna be off the slides. Learn Smart was due on Sunday. You guys all did it, thank you. Make sure we do the next 2 Learn Smarts. Remember, we're trying to do this ahead of the topic, right? So Learn Smart 1 is all about topic 1. Learn Smart 2 and 3 are going to be about topic 2, which we're going to start covering next week, right? And we have our homework for topic 1 that is due on Sunday, right? So we've got a couple assignments due on Sunday, right? So make sure you stay on it. If you have any questions about the homework, make sure you come to my office hours or shoot me an email. make sure you get it answered, right? Prefer that you come to office hours. Office hours are after this class from 3 to 5 today, Friday from 3 to 5, Tuesday from 3 to 5, right? So Tuesday, Wednesday, and Friday from 3 to 5 p.m. or Monday mornings from 9 to 11 a.m., right? So just make sure, and anything outside of those times, you can, shoot me an email and see if I'm available. I'm definitely willing to meet with you guys whenever. Well, not whenever, but you know what I'm saying. Right? Obviously, if you try to get in touch with me at 11 o'clock at night, it's just not going to happen. All right. So today we're going to go over motion of several particles, graphical solutions, curvilinear motion, and rectangular components. Okay, so that seems like a lot, right? But it all connects, right? So last week we focused simply on a single particle, right? A single particle moving, right? And we did a few problems, right? And most notably was the problem where we were running around outside of GCU, right? And the lights went off, but that's fine. So where you're running around GCU and we had to figure out how far we went in 15 minutes and then how long it took us to get back to campus if we started running from a dog that was chasing us, right? That was the big problem we did last week. So what about motion of several particles, right? So some systems that we experience in our day-to-day life, right, consist of multiple parts, right? And each one of those parts can be considered a particle, right? So we might be interested in how several different particles move when they're connected to one another. And the obvious example here is this pulley system, right? If you have a pulley system, all of these masses are connected through this cable, right? And so if you move one of those masses, the other two are also going to move, right? Like if I pull down on A, right, potentially B moves up and C moves up, right? That's how there would be some relation between those particles, right? So when we have several particles that are connected together, they might affect the motion of one affects the motion of the others, right? So in order to talk about this in a mathematical sense, we need to start talking about relative motion, right? So I have particle A here on my number line, right here, and I've got particle B, right? And we're measuring it from our origin here, right? So the distance to A is XA and the distance to B is XB, right? And the relative position of particle B with respect to A is X sub B, right? So this distance minus this one. So we're trying to figure out if I was at particle B and how far would I have to go to get to particle A? Okay, now this might seem trivial, right? Because you're like, well, yeah, obviously it's just B minus A, right? But you can also define it the opposite way, right? Because remember, position is a vector quantity, right? And because it's a vector, it's got size and it has direction. So me going in this direction, although the distance might be the same, is different than me going in the other direction, right? Because one of those is positive and one of those is negative, right? Just keep that in mind, right? So typically the notation is, right, when we have this is saying the relative position of B with respect to A, meaning that I'm starting at B and I want to know the path that it takes me to get to A, right? Right there, right? You can also define X of A with respect to B, right? So if I'm at A and I want to go to B, right? Okay. What happens if we take the derivative of that, right? Well, all right, well, first off, what if we just wanted to find XB? Well, you can also write this equation, right? So you just rearrange this relative position equation, right, and solve it for X sub B, then you've got XA plus X of B with respect to A, right? If you take the derivative of this, which is the whole focus of last week, right, where you can take the derivative with respect to time of this equation, and we get an expression for the relative velocity. And this is saying, I want you to think about this as well, right? So for velocity, right? If we're saying we want the relative velocity of point B with respect to point A, Imagine that I am standing on point B and I'm watching point A move. That is the velocity that we are talking about, okay? Right, so you exist at point B and you're watching point A move, right? That's another way of kind of conceptualizing this, of thinking about this. So, right, V of B with respect to A is just VB minus VA, and we can rearrange it again to get our VB equation, right? The acceleration of B with respect to A, same thing, we take the derivative again, right? Now, are we ever gonna have to go the opposite way? No, we would, in this class, we're never gonna integrate these, right? You're gonna kind of treat these as known equations that we just kind of manipulate and use. For the foreseeable future, we're not going to really tackle a lot of these relative equations, but they become really important when we start talking about rigid body motion, which is going to be in a couple of topics from now. It's not to say that they're not important right now. It's just that the methods that we use to start with don't really focus a lot on these, right? And we'll see a couple of problems where we use them, and I'll show you, you know, how we should do so, right? But just keep that in mind. You guys have any questions on relative motion so far? So why would relative motion be important, right? So that's a good question. So I want to analyze this system, right? I want to know how X of A is moving, right? But I was only given measurements for XC and XB, right? But I know that this moves in relation to the others as well, right? And so you can start to put this all together. And we'll do a problem like this where you can see why this is relevant. Any questions so far? Just doing okay? Everybody tracking maybe? Maybe. All right. We're gonna keep going. All right. So we're actually just doing an example. Let's just show it in action, right? So what do I have here, right? So imagine for a second that a ball, right? I'm standing in an elevator, and just like everybody loves to do, I'm going to throw a ball straight up, right? Because, you know, who doesn't do this when they're riding the elevator, right? It's so boring to ride the elevator. It takes so long. You need to fill that time with something, right? So you're going to throw a ball vertically, right? Starting, and somehow you're managing to float 12 meters above where the elevator starts. Okay. So you're throwing, the ball is launched from a position that is 12 meters above the floor of the elevator, right? And you throw it vertically with an initial velocity of 18 meters per second. At the same time, this open platform elevator starts to pass through the 5-meter level, right? And it's moving upward at 2 meters per second. We want to find two things. We want to find when and where the ball hits the elevator and the relative velocity of the ball and the elevator when they make contact, right? So we're trying to figure out what time and at what, so it's really three things, but under 2 bullets, right? We need to find the when. So how long does it take for the ball to hit the floor of the elevator, right? So presumably, right, presumably you throw this up and gravity would say, right, it goes up and then it comes down, right? And we want to figure out where in space this hits. Okay, so let's try it, right? Let's try it. So how do we start? How do we start? How do we start? Well, the way that we're going to start this is that we're going to draw a picture. Well, we already have a picture, Dr. D, so mission accomplished, right? Well, yes and no, right? Sometimes it's helpful to try to understand how this is going to look like through its entire cycle, right? So if this is the floor of my elevator, right, at the start, it's starting at point O, I'm going to say that this way is positive upward, right? Positive Y and positive X, right? So I've got my coordinate system here. And we're gonna assume this is thrown straight up. So what we'll have is that the ball will start to come up, it will reach its peak, and then it will fall, right? And at some point, the elevator this whole time is moving up, right? And then the elevator comes up, and at some point, these two occupy the same place, right? That's why they hit. Okay. So there's a couple of things that we know, right? And they're given to us right in this diagram, right? We know that the velocity initially is 18 meters per second, right? So this initial velocity here is 18 meters per second. We know that the acceleration is negative 9.81 meters per second squared. Now, is that changing or is that constant? Is that acceleration variable or is it constant?
Doesn't it change noticeably with large changes in altitude?
Does it change? Does the acceleration due to gravity change? Zach?
Maybe I'm thinking of the force at least. I thought there was like some sort of difference like, between what's pushing.
Sorry, I'm having a little trouble hearing you.
Okay. Like I thought, like on Mount Everest, like the amount of gravity you're experiencing is like less than sea level.
So, okay, we're assuming that, this is like just this, not at the top of the highest mountain in the world, right? This is not, it's not the elevator it's not the Elon Musk space elevator, okay? Which that would be a really good place to build it, right? Because you're already you're basically there anyway. Okay, just a normal elevator, right? Under standard conditions, right? The acceleration of gravity would be considered constant, right? We all agree on that? Yeah. We typically call it the gravitational constant, so that's a thing. So, okay, this is a constant acceleration, right? This is a constant acceleration. So because it's a constant acceleration, that means that right off the bat, we know we can use our pre-canned kinematic equations that you don't have the sheet for yet, but you will after class today, right? All right, so let's start looking at some of this, right? So for the ball, right? Because I'm going to start here by looking at the ball first, right? And if we had our kinematic equation sheet, which I have mine, which doesn't help you guys, but I do have mine. Right. So if we start with the ball, right? Well, what do we know? We know that the velocity of the ball is equal to the initial velocity plus the acceleration times the amount of time that it takes to travel, right? So how do we know that? Well, if we're given initial velocity and we're looking for time and we're given acceleration, right? We can, I'm sorry, if we are looking for the final velocity, we're giving acceleration, initial velocity, and oh my goodness, my brain is not on point today. I apologize. Start that over, right? So there's two things. We need to know the final velocity of the ball, right? And we need to know the position where it happens, right? So if we write the equation for the ball here, right? Looking for the final velocity of the ball equals the initial velocity plus the acceleration times time. We know the initial velocity. We don't know the time. We don't know the velocity of the ball final, right? But we do know the gravitational acceleration is negative 9.81. So we're left with this equation here, right? Where we still don't know this, and we still don't know this, right? So we have two unknowns. Two unknowns means we need two equations to solve it, right? We're going to create a system of equations here. Okay, so we go back to our kinematic equation sheet, and we remember, well, we were asked to find when, right? Our problem statement says we need when and where the ball hits the elevator floor. Okay, right? So I should probably look for a distance, right? So I've got y sub b, right? And y sub b is equal to the initial position of the ball plus the initial velocity times time plus 1/2 at squared, right? 1/2 times the acceleration times time squared, right? Remember, we went through the derivation of these a little bit last class, right? But these are just from our equation sheet, right? We've assessed what we have and what we don't have, and we can determine what equations we need, right? And in this case, well, what do we have? What do we know? Well, I don't know. Well, what do we know, right? What do we know? Well, I know 18. I know my initial position is 12, right? The ball started at 12 meters, right? But hey, I still don't know y sub b, right? I don't know where the ball is, and I don't know the time. So that seems problematic still, right? Because all we did was add another variable, right? How are we going to deal with this? Well, that was just looking at the ball. Now we have to look at what the elevator does, right? Because these two things, although they're not physically connected, right, they are going to collide at some point. And we can figure that out. We know that the velocity of the elevator is constant. It's 2 meters per second, right? The problem statement says it moves at a constant 2 meters per second. This implies what? What does this mean for us? If I have a constant velocity, what does that mean for my acceleration? What is my acceleration?
0.
0, right? If you take the derivative of a constant, what is it? It's 0, right? So the acceleration of the elevator is 0 meters per second squared. Another way of thinking about that is if my velocity for my elevator is constant, there's no rate of change of my velocity, right? The rate of change of the velocity is the acceleration. So we can write down our position equation. I can figure out how far my elevator has moved, right? I can figure out how far my elevator has moved based off of the initial position of the elevator, which we know is 5, right? Because we're told that it starts as it passes through 5 meters, plus 2 times t, right? My initial velocity or my acceleration, the velocity of my elevator times time. Well, that's great. Well, I've got 3 equations here, right? I still have 3 equations, but I don't have any way of, right? I've just added another variable, haven't I? Right? Because ye, this is still unknown. That's still unknown. So if I count up all my unknowns, I've got 4. Right, so right, feels like we're kind of we're spinning our gears here, right? We're not really making headway. Yes and no, right? Because we just talked about the relative position of something, right? So we're going to bring that in, and I'm going to say, well, the relative position of the ball with respect to the elevator is just yb minus ye. And here's our 4th equation, right? And I can pull this in because I know what yb is, right? YB is just this equation up here, is equation 2, right? Y sub b, I'll just write it here, right? This is equation 2. And y sub e, we can substitute in equation 3, and we can subtract those 2 things, right? And what are we left with if we do that? Well, we get 12 plus 18t minus 4.905 t squared minus 5 plus 2t. And I have it equal to 0. Why would I have that equal to 0? Why would I have that equal to 0? What do you guys think?
Because they meet up.
I'm sorry, say that one more time.
Because they meet up eventually. So the distance has got to be the distance traveled.
Then also isn't
So
acceleration the derivative?
remember what we're looking for. You're almost there, right? You're almost there, right? Remember what we're looking for. We're looking for the point where they both hit, right? If we go back to our relative, position graph here, right? Now imagine for a second, right, that A is the elevator and B is the ball, right? We want to know when these both are at the same point, right? Because they've just hit each other and they're touching. if they're touching, what does that mean for our relative position? So if we draw it, right? Here's point O. Here's the elevator. Here's the ball. This is the point when they touch. What does that mean for my relative position? What is y of b with respect to e? Well, that's just going to be yb minus ye. But when they're touching, yb and ye are equal, right? So the relative position when two things are in contact is 0, right? The relative position between these two things when they're touching is 0. Right? That's a big idea. It's a big idea because it allows us to solve this equation, right? And this just becomes, you know, a quadratic equation. So we use our quadratic formula like we did last class. We throw it in your calculator or use your favorite method, right? And if you solve for it, you'll get two values for the time because it's squared, but one of them will be negative, which we all know is impossible unless, you know, you are one of the iterations of Doctor Who or another Time Lord that is yet to be named, right? And we're left with 3.65 seconds. Okay, so we solve this, we get 3.65 seconds. What is that? That's the time, that's how long it takes us to hit. It takes the elevator to hit the ball. We need to know where in space we're hitting, right? And so how do we figure that out? Well, we're going to take our equation 3 here, and we're going to plug in 3.65, right? This is just equation 3. We plugged in 3.65. We crunch those numbers, and we find out that the elevator at 3.65 seconds has traveled 12.3 meters. So the ball hasn't gotten that far, right, from its initial spot before it hits the elevator. Right? Okay. And then the final question that we were asked, right? So that's the when and where. Then we want the relative velocity of the ball with respect to the elevator at contact. So how do we do that? Well, the velocity of the ball with respect to the elevator is what? Velocity of the ball with respect to the elevator is just the velocity of b minus the velocity of e, right? How do we figure out the velocity of b? We already did it. It's this equation, right? They're specifically asking us to figure this out at 3.65 seconds, okay? What's the velocity of e? What's the velocity of e? What's the velocity, you guys? It's written right there. How fast is the elevator moving?
Meters a second.
One more time. I'm having trouble hearing everybody today.
I mean, the elevator's moving at a constant rate of 2 meters per second, right?
Oh, shoot. Sounded like you said 2 meters per second.
Yeah.
Yes. Okay, good. Sorry, I
Sorry,
can't.
my mic has been.
The volume is really low in here, and I have it jacked up as high as possible. So it's hard for me to kind of hear. I apologize for making you guys repeat yourselves. I know it's frustrating. All right, so it's 2 meters per second, right? We were told it moves at a constant 2 meters per second. So we take, if we wanted the change in velocity, right, the relative velocity between these 2 points, we just take velocity of b minus the velocity of e. We plug in 3.65 seconds here, right? And we're left with negative 19.81 meters per second. Why is it negative? Well, because it's moving downward, right? Remember, it's a vector, it's moving down. All right. So are you guys following? Are we okay? We have major issues? You have any questions?
I mean, when would you know which formula to use for different scenarios?
That is a great question. How would you know, right? So each one of these is written in a general way. So I'm gonna,
'Cause, yeah, we did them in physics, but it's been a while, so I just kind of need a refresher.
right. Let me show you guys something. This might help if we do this. Let me grab them. This would probably be a good idea. Give me 1 second. I'll get them up here. Okay. Oh, they're not all, there we go. Oh, they're gonna animate. So fancy. So fancy. All right. So how do we know which ones to use, right? Well, in the general case, right, we can always just write these down, right? So, I mean, you can rearrange these in different ways to solve for different things, right? But if we go back here, right, remember we were looking for V sub B, right? Remember, we needed velocity of the ball. Well, then we should probably use this one, right? To get the position, instead of using X's, we're using Y because we were talking about vertical instead of horizontal, right? This equation down here, right? This is, if we don't know how much time it takes, but we know how far we've gone and we know the acceleration, right? That's velocity as a function of acceleration and position. Yeah, take a second, copy those down. They're going to be useful for the rest of class today. All right, so everybody just take a minute, get those written down. All right, because we are going to go into Dr. D's favorite topic in all of dynamics today, right? Which is projectile motion. We'll hit it a little bit today. We'll really do a lot on Thursday. We're going to do, we're going to do an in-class experiment via Zoom somehow. And it's going to be great. It's going to be great. I think it's going to be great. I think you guys are going to have a lot of fun. But anyway, all right, did I waste enough time by rambling that everybody's had sufficient time to copy those down? Yeah, okay, good. That's what we call in the professor business, that is called a stall tactic. All right, anyway. So that's the basics of relative motion, right? We can exploit relative motion as an extra equation, right, to build systems of equations. Now, this class, a lot of the stuff that we're going to do is setting up systems of equations, right? We're going to end up solving two or more equations simultaneously, right? And you can do it a couple of ways, and whatever your favorite method of doing it, that's fine. I'm not going to explicitly go over how to do it in class. If you guys have issues and you want to know more about it, we can certainly do it outside of class, and you can come to office hours and we can go through that, okay? So if you're feeling less than confident about some of these things, please come to office hours and we'll get you straight. All right. So dependent motion, right? I hinted at it a little bit, like when you have these pulleys, they're all interconnected in some way, right? Okay. So the position of a particle can depend on the position of another particle if they are connected like by a cable, right? Now the easiest way for me to illustrate this to you guys is everybody has worn or does wear shoes with laces at some point in their life, right? You guys are all familiar with shoelaces, right? Okay. Have you ever had the annoying thing happen where one side of your laces is shorter than the other? Yeah. But the entire shoelace is still the same length, right? It hasn't changed the length. Like if you were to take it out of your shoes, it's not magically shorter, right? If it was, this is going to be absurdly long for the sake of illustration, but if you had a 3-foot long shoelace, right, like that, which is ridiculous, but if you had a 3-foot long shoelace, doesn't matter how many eye holes you put it through, right? It's still 3 feet long. Same idea with pulleys, right? With this cable, right? This cable that's traveling all the way around here, right? If we were to take it off of the system, has a constant length, right? It is simply some length of cable. It's just that it's winding around, right? So it's traveling some path. That's important, right? Why? Because if I had a system of two particles that are connected, right? I could measure the distance from that particle up to some set point. Now it doesn't have to be, it just has to be some static point, right? Something that's not changing, right? So we know this distance, x sub a, right? From here, let's try that one more time, right? We know this distance from here to here. And we know this distance from here to here, right? And we can say, well, both sides of this pulley, right, are both defined by x sub a, right? So if I wanted to know the entire length of that cable, it would just be x sub a plus 2 times x sub b, right? Because I misspoke, right? This side here is x sub b on both sides, right? This length of cable here is x sub b, right? Everybody cool with that idea, right? So we can take these segments of cable and we can add them up and we'll get the constant, right? So it's equal to some constant, right? So x sub a plus 2xb is equal to some constant. Well, what if I had a third thing on there, right? What if I had a third particle attached here, right? And you can see it in this diagram that's on the other side, on the right-hand side here, right? Let me move y'all pictures, right? And again, right, we've got, oh, again, we've got x sub a, right here. We've got x sub a over here. We've got x sub c on this side, but we have two lengths in the middle that are of length x sub b, right? And so we've got two, or I'm sorry, we've got two x sub a's also, right? So we've got one here and one here. We've got an x sub c here and two xb's, right? So that's an entirely constant length as well, right? 2xa plus 2xb plus xc. Okay, so is everybody comfortable and okay with that for right now? Are we seeing how that works out, right? The thing that kind of sticks with people a little bit is that, well, that's not really the length of the cable, right? Because you're measuring from the top down to the particle, so it's technically not the same thing. Well, yeah, you're right. It's technically not. You're overestimating a little bit, but it allows us, because it's from a set point, right? That's set, right? That the ground up there, or the roof in this case, right? Because of that, the change in that position is still going to characterize our velocity, right? Because we're measuring them both from the same starting point, okay? As long as everything is measured to the same starting point, those changes in positions will represent your velocity, right? Because they all have that additional amount that is the same starting, okay? All right. Is everybody right? Throw up a reaction, something in the chat. You guys are a bit dead today. Right? It's a bit dead today. I realize you're not here and everybody's on mute, and all I hear is the HVAC in this room. But come on, be a little. Some signs of I know it. It's probably post lunch coma. It's probably what it is. That's what I'm guessing. Post lunch coma. Thank you. All right, so we're okay then, right? I'm assuming we're okay. I'm assuming that if there's something catastrophic happening, right, you guys will let me know. Let's do that too. All right, so if I want the velocity of either of these, right, how do I do that? The same way that I get the velocity of any position, right? I take the time derivative. Okay, so if I take the time derivative, let's focus on xa plus 2xb. I'm going to take the time derivative there, right? Well, that's just going to be dxa dt, which is what we call v sub a, right? So if I'm going to take the time derivative, that's going to be v sub a, right? So I don't really have a good place to write that. Oh, that's not correct. I don't really have a good place to write this. So we're going to do it over here, just so everybody can kind of see. All right. Oh, of course I grabbed the wrong one. talking about this guy over here, right? So I'm going to take the time derivative. And so we remember that that arrow means we're going to take the time derivative, right? D dt, right? So d dt of x sub a, well, that's just v sub a plus d dt of 2xb. Well, the 2 is a constant, so that can come out. So that's going to be 2vb, and that's equal to the derivative of a constant, which is 0. So now I have an expression for the velocity. What if I want the acceleration? Well, take the derivative again, right? If I take the derivative again, I'm left with that, right? So now, right, this one that's written out on the bottom here, that's for our other system, right? 2xa plus 2xb plus xc is equal to a constant, right? So surely it can't just be as simple as we just did for only 2 particles, right? But it is, right? We're just going to take the derivative again, right? We take the derivative of each term. We'll end up with 2VA plus 2VB plus VC is equal to 0. And we take the derivative again. We get 2AA plus 2AB plus AC is equal to 0. Okay? It's just, it works out. It works out just like, okay? So let's put it into practice, right? Let's put this into practice. So here's a typical problem that we would have, right? There's a typical problem that we would have involving collars and pulleys, right? And let's take a look at this, right? So this pulley, it's pulley D here, right here. Hold on. Let's do that. This pulley D, right? Notice it's not fixed like the pulleys C and E. It has a collar, right? And this is going to let it slide on this post, right? And we're going to assume that it's, frictionless collar, right? So that it slides really nice and easy and doesn't impede our motion at all, right? Attached to this is this mass B, right? This mass B over here, which comes up around pulley E, right? That goes around D, comes around C, and then it gets attached to this collar at A, right? And the collar at A just slides up and down the bar as well, right? Okay. So pulley D is attached to the collar, which is pulled down at 3 inches per second. Okay, so we know something, right? We know to start with, that this has a velocity equal to 3 inches per second. At time equals 0, collar A starts moving down from point K to point L, right? So it's going to move 8 inches starting at time 0, right? So our initial time point we're saying, okay, is up here at K. A is up at K. It starts moving down with a constant acceleration. Okay, well that's helpful, right? That's helpful for us. So it moves down with a constant acceleration and 0 initial velocity. Okay, so we can say that point A has initial VA naught equal to 0 inches per second. We can say that. We also know that once the collar reaches point L, right? So at some other time, it's going to be here. And when we get there, we're going to have 12 inches. V sub A here is 12 inches per second. And we know it's downward, so it's going to be negative. We want to determine the change in elevation, the velocity, and the acceleration of block B. Right? So presumably, if this moves down, right, if A moves down, then B will do what? What do you guys think? Is B going to move up or is B going to move down? If I pull down on A, what should happen? Do you think it moves up or do you think it moves down? No takers? No, don't be afraid. Just unmute and say up or down, guys. Say it. It's cool. You can do it.
That's if the A is moving which direction?
Downward.
I would say up.
Yeah, I think that would be the
Wow.
case as well, right? If this, so remember, both of these are moving down. D is moving down and A is moving down. If both of those move down, there's not enough cable left for B to move down, right? This is gonna go down. At some point, that's gonna pull this down, right? That's gonna wanna pull this up, but this collar D is also pulling down. So both of these together are moving downward, so B has to be raised, right? And in real life, right, you would have a system like this to do what, right? Well, you would want to be able to multiply the force that you're putting in on the front to be able to lift that mass, that crate, whatever that happens to be, right? What looks somewhat like an anvil, right? In the Looney Tunes space, right? This would be, you would have, your Roadrunner running under here, right? And you're trying to drop the weight on them, right? But okay, anyway. So what do we do? How do we do this problem? Right, so it's always helpful whenever we do any problem, right? We're gonna find, we write down what we're gonna find, right? So we wanna find y sub b, we wanna find v sub b, and we wanna find the acceleration of b, okay? When do we wanna do this? Well, when collar A is at L. That is our when, right? This is defining our time. So one of the first things that we're going to need to do is figure out how long does it actually take A to get all the way to L, right? Presumably. Well, really, that's, what do we know? Well, we know that this is a constant this has a constant acceleration between the 2 points, right? And we know what the change in position is. So if we're gonna go back to our, and I will just this once, go back here. So which one of these equations do you guys think we're gonna use? We are looking for acceleration. We know velocity, initial velocity, we know final velocity, we know initial position, and we know final position. Which one of these are we gonna use if we're looking for acceleration? Which one of these are we going to use?
The second one, perhaps?
So we don't know the acceleration, right? And we don't know the time it takes either. We are going to need that second one to find the time, but the first thing we need to do is find the acceleration. But that's not a bad, you're not wrong. You're just not looking at the whole picture, right?
So why don't we use the derivative of the velocity? Do we have the velocity?
All right, so let's try this a different way, right? So right now, what are my knowns? The things that I know, absolutely, right? I know the initial velocity of point A, right? We were told that that is what? That was 0 inches per second. I know the velocity of point A when we pass through L, right? Which we'll call the final velocity, right? So I know V naught, right? I know V naught. I also know V, right? Because we're given both of those. We know X and X naught because we're starting at 0 and we're going to move 8 inches downward. Okay. But I don't know A. I want to highlight both of those. So I don't know A and I don't know T, right? Man, this pen is not great. But anyway, you get the point. I don't know A and I don't know T. Which one of these equations allows me to directly solve for a variable? Which one of them only has one thing that's unknown?
The third one.
The third one, right? Exactly. Right, so if you use this third equation, you can immediately get the acceleration of point A. And if we know the acceleration of point A, then we can plug that back into the second equation to figure out how long it took us, right? To figure out how long it took us. So that's where we want to be. Okay. So we write down our equation, right? We got VA squared plus V, I'm sorry, not plus, equals. I'm getting all ahead of myself here. VA naught squared, right? So my initial velocity plus twice the acceleration of A times, I'm going to call it YA. You can call it XA, it doesn't matter. It's just a variable name. Okay. All right, so we've got 12 squared, where I plug in some numbers, is equal to 0 squared plus 2 times A sub A times, well, this is 8 minus 0, right? Because it's the total distance we're moving. We're starting at 0, we're moving 8. So this gives me an acceleration, if I solve this, as 9 inches per second squared. And we know it's constant, right? We were told that it was constant. We have acceleration of point A of 9 inches per second squared. So we can take that to our second equation that was on that sheet, which tells us that the velocity of point A is equal to the initial velocity plus the acceleration times time. Okay. And if we plug some things in here, right, we will get that 12 is equal to 0 plus 9 times t. And we can solve this, right? So t is equal to 1.33 seconds. So that's how long this whole process takes, right? It takes less than 2 seconds, less than a second and a half, for us to pull this thing down by 8 inches. Okay. So now what, right? How does that really help us, right? How does that really help us? Well, we're gonna move on down the line here, right? So we started at A, right? We started at A, now we're gonna look at D. We're gonna see how is D moving, right? What can we figure out about D? Well, what do we know about D? We know that D is attached to a collar that is being pulled down at 3 inches per second. So it has a velocity that's constant of 3 inches per second, right? It's being pulled down by 3 inches per second. So look at our position. We want to know how far that this has moved in that time. Why do we want to know how far it's moved? Well, remember, the thing that's coupling everything together, right? The thing that's coupling everything together here. And I'll go back to my diagram again, right? Because I got to bring this back in, right? The thing that's coupling everything together here is what? Well, it's the length, right? The length of these segments, right? If you call this from here to here y sub b, and you call this guy from here to here y sub d, then we've got a second y sub d here, and we're going to call this, we're going to call that y sub a, right? So remember, the thing that's holding the glue that connects all these particles together is this cord, right? And we're trying to figure out how does each of these segments change, right? And so y sub a plus 2y sub d plus y sub b is going to be equal to some constant, right? Some constant. That's supposed to be an n, not an m. It's fine. It's good. It's good. Constant. Okay. So what we need for point D is we need to figure out this y sub d, right? Because I know y sub a, right? I know what y sub a is. I know the change here, right? I know that this starts at 0 and it finishes at 8. I know I want to know how much this moves in 1.33 seconds. When this gets to K, when this goes from K to L, right? When this Y sub A is 8, how much have I moved that collar D, right? So that's why we're working with this equation, which is BD sub T. Okay, I can rearrange this a little bit, and I can say that YD minus YD naught is equal to the velocity times time, right? And there's a reason that I want to do this here like this, because this describes what? This quantity, when I have the initial, well, if I'm subtracting my initial position from where I was, right? So let's look at our number line again, right? I started here. This is going to be YD naught, right? My initial position. And I move here to Y sub D. This change in distance, let's call it delta Y sub D, is just what? It's YD minus YD naught, right? So this, we're gonna call it delta Y sub D. I'm actually not gonna find the total distance traveled. Well, I'm not gonna find the exact position that we're at. I'm not gonna find Y sub D. I'm gonna find the total distance that we traveled for point D using this. And that's gonna be equal to what? Well, that's 3 times 1.33, which, as we all know, obviously without using a calculator, is just 4 inches. Right. Everybody can do that there, right? Okay, so I've got this distance of 4 inches, right? And because we've assumed that our cable is inextensible, right? It doesn't extend, it is one length, right? We can write down our equation, right? We already wrote part of it, right? So YA, not plus, not equals plus 2YD, again, not an equals, plus Y sub B is equal to some constant, right? But much like your shoelace when it's out of place, right? Much like your shoelace when it's out of place, it's still, right? If I was to pull your shoelace, so one side was longer than the other, right? Thereby changing my, and we'll say that, you know, that's our final position, right? This is out of place, that's our final position. But the total should still be equal to the initial position of when it was perfectly in line, right? So you can have my initial Y sub A plus my initial Y sub D plus my initial position for B, okay? So imagine this for a second. We're talking about 2 different points in time, right? This initial is when A is at K. And this part on the left-hand side is when A gets to L, right? Okay, all right. Is everybody with me so far? Is everybody okay with how we've set this up so far? Yes, no, maybe so.
I'm gonna go back to when you got the, I think how you figured out the time.
How did we get this time? 1.3.
Yeah, I think I missed that part. Okay, yeah.
Came from here, right? So what we did was the whole point of doing any of that finding that acceleration of point A, the whole point of that, Zach, was so that we could then plug that in and figure out how long the entire process takes. Because the time, right, and we'll see this with projectile motion as well. Really, a lot of these particle problems with dependent motion, it depends on, you really want to start off with finding how long it takes for an event to happen, because that's going to define your other equations, right? Because then you use that time to evaluate another equation, right? Because you're saying, well, I know that I want to evaluate this at 1.33 seconds, right? So you'll find that a lot of these problems end up boiling down to, all right, let's find the time it takes for something to happen. Let's take that time and plug it into another equation to figure out how far we've gone, to figure out how fast we were going at that time, right? Those are the kind of things that we're trying to, that we're going to end up doing. Good question. So then when we get to here, right, this is just, let's think about this like this, right? This is when we are at L, and this guy here is when we are at K. The total length of that chord doesn't change between those two times, but the individual segments might. And there's a reason why we wanted to do this. And it kind of leads back to what we drew on our number line up there, right? Our points. Because again, we're not really concerned with the actual position in space that we've moved to. We want to know how much did we change from the starting point. So if we do a little bit of algebra, right? If we do a little bit of algebra, right, and I subtract the right side from the left, I can get this equation. And now, right, if I wanted to, I could put parentheses around these. I could, just to make it look nice, for nothing else. I guess it would be for order of operations, right? But what do I have? Now I've got the change in particle A plus twice the change in particle D plus the change in particle B is equal to some constant, which is 0. 0 is a constant. So what do we do? Well, we can take this, right? Well, what's the change in position of point A if we go from K to L? What was that? What do we got? We go from K to L. What's the change in position?
Just
For point A, what's the change? If we're going from K to L. What do we start at?
well, if it's point A, that's the collar, right?
Yep.
Yeah, then if it's going to K to L, that's 8 inches, is it not?
Right. Exactly. Right. So this, we can plug in 8 plus twice YD minus YD naught. Well, we calculated that up here, right? That's just 4 inches. And I'm going to call this delta Y sub B because I don't feel like writing YB minus Y naught. Right? That's equal to 0. Now I can solve this for the change in the position of B, right? And if I was going to do this out by hand, right, I would do my algebra. I would say this is then equal to, well, I would subtract 8 plus 8 is 16, right? So this is negative 16 here. Yeah. So, right, so 8 plus 8, this is 16 plus delta YB. I just move the 16 over to where the 0 is, right? By subtracting, and I'll end up with negative 16 inches. And you're going to say, well, Dr. D, that doesn't make sense. It's not moving downward. Well, if we look back at our drawing, we'll actually see that down was considered positive for everything that we've been doing, which is annoying, right? But it's fine. Just make sure you remember which way you've designated as positive and negative, and we should be okay. Okay. So this is going to be moving up by 16 inches, which is what we expected, right? We expected that if we pulled down on A, B would go upward. Great. That makes physical sense to us, right? Okay, so that's how we found y sub b, but we still need to find the velocity and the acceleration of point B, right? So how are we going to do that? How are we going to do that? Okay. Well, it all has to do, right? It all has to do with the first half of this equation right here. Okay. Before we start doing that, is everybody okay with this that's here on the page? Is everybody following so far? Do you have any questions? Okay. Okay. Hopefully I have another slide in here. I didn't do it. We are not going to do the pulley activity today, unfortunately. That one's one that we have to all be in class. We'll do it when you guys get back to campus in a couple weeks. The activity for Thursday, you guys don't need to all be in class, and we're going to make it work. But the pulley one, unless you guys all have some pulleys around your house, it's going to be pretty difficult. So we'll just wait until we get back to do it. I think it'll still be fun to do. Okay. I'm gonna add a slide here just so we can finish this up. Give me 1 sec. That's not good. Okay.
Just a quick
Yeah, it's up.
question. I guess I missed where the 4 came in. Because I didn't see that in any of the other parts.
Okay.
Is that the change of y not 3 times
The
1.33?
4?
Yeah.
That 4 that we put in the 2 times 4, that's from above. We had the change in y, right?
Okay. That's from 3 times the time.
Yeah.
Okay.
Right. So, yeah. Unfortunately, when I exited to put a new slide in, guys, it did something really awesome, which is it cleared all of the work that I did on this problem, which is super fun. So if you have any other questions, feel free to ask, and we can certainly go through it again. I will just have to rewrite some of that work. It's not a big deal. Technical difficulties, right? What's the other motto? Fall 2020. It's not as bad as I thought. / technical difficulties / unmute yourself. Right. That's the other. That's the third motto for the semester. All right.
Flash, is my audio working?
Yeah. You guys hear me? Can you see this? Can you see the slides? All right. So we're gonna be using this equation again, right? This is the constant, right? This is equal to a constant, right? Just some constant length. Doesn't matter what it is, no, right? Because why? Because we are going to take the derivative of this with respect to time. And by doing so, we will not only get an equation for our velocity, but we will also inherently change the color of the equation. Because I have 4 different colors to use, and I'll use them how I want. Okay. So we can plug some stuff in here, but we're not going to do that just yet, right? Well, actually, no, I take that back. We're going to plug some stuff in here. So do we know what V sub A is, right? Yeah, that was given, right? So this is 12 inches per second. What about the velocity of point D? Yeah, that was also given at the very beginning, right? That was 3 inches per second. Sorry, that was 3 inches per second. So 2 times 3 inches per second. Plus the velocity of point B is equal to 0. Okay. Well, we can solve that, right? We'll just solve that again. So 12 plus 6 is 18. So That's 18. So the velocity of point B is negative 18 inches per second. And that seemed fairly reasonable, right? It's also moving up. That makes sense. It's going to be, if we're pulling it upward, it's going to be accelerate. It's going to be having a velocity upward. Cool. So we'll take the time derivative again to get the acceleration equation, right? Okay, well, we can plug some things in here. We found earlier that the acceleration of point A was 9 inches per second squared. We know that we had a constant velocity for point D, which means we have a 0 acceleration there, right? And we've got A sub B, that's equal to 0. We can solve this, right? So whenever we multiply something by 0, we just get 0. So that's awesome. And we're just left with negative 9 inches per second squared. Okay. So where's the hang up here, right? Where do people typically go wrong, right? In the setup, right? A lot of these problems, right? A lot of these problems, the trick is in the setup. Once we get everything set up, the rest of it kind of just melts away, right? But the trick is getting it set up. And where does that come from, right? Where do we get better at that? Well, that comes from us practicing, right? And doing homework problems and trying problems from the book, okay? I know people get really antsy and anxious, and they spend a lot of time worrying about exams, right? Or quizzes. In this class, we don't have exams, we have quizzes, right? Even though it's really the same thing, it's just a different word that people don't get as anxious about, right? So let's not call them exams. I don't want you to freak out. They're quizzes. So in the quizzes, right? Like, how do I study for the quiz? That's a great question, right? How do you study for the quiz? You do practice problems, okay? What is the quiz going to look like? The quiz is going to be the same format as your homeworks, right? It's going to be problems that you do, right? That's what it's going to be. These kind of problems are neat. I like these problems, right? They harness a lot of different things, right? You're going to have to do some differentiation. You're going to have to understand how things are moving physically, right? These are nice problems. They're tidy. We also know, you guys have also been told that I like projectile motion problems, right? So, you know, there's a lot of cool stuff that we can do with this, but you guys need to really do the practice, right? To get comfortable with some of the stuff and ask questions, right? Those would be my key piece of advice: practice and ask questions. The other thing is, and this is something that students have told me is not very helpful, but I think it's an extremely helpful piece of advice. You should treat the quiz like a Dementor, right? And you should, the way that you beat a Dementor, right, is you face the thing that you fear the most, right? Whatever you think is the hardest thing for you to understand, imagine that that is definitely going to be on the quiz, okay? Spend most of your time studying the things that you think are difficult, right? Because if you already know how to do something, you're wasting your time that you could be spending on shoring up your knowledge of another topic, right? So just keep that in mind, okay? Now, we don't have a quiz for, you know, a few weeks, so don't stress, right? But, you know, treat the homework as practice. Make sure you're understanding how to do those things, okay? Are there any questions on this problem? Or anything else that we've done so far today? I know it says next that we were going to do our pulley thing, right? We'll do this when you guys get back. It just, as much fun as it would be for you guys to watch me play around with a system of pulleys, right? I think we would be better served if you guys did this when we got back. Okay. Any other questions, comments, concerns? No, maybe. Just no, everybody's doing all right. All right. I'll stop asking. All right, so let's talk about graphical solutions, right? So sometimes people will, like, your boss will walk into your office and just throw a graph down right, and say, get this to me, like, tell me what this means right now, right? Because that's not really what happens, but you can imagine a certain scenario where you would be handed a graph, right? And then when we do testing, right, when we do real life stuff, right, we often plot our data versus time, right? And right here, what we have is the acceleration versus time from a head impact during a round of boxing. Now, let me ask you this. When do you think the punch was thrown?
Around 47 seconds. No, thrown around. Well,
Right, so remember, this is the head, the impact of the head on the head, right? So the head gets hit, right? So probably the impact, probably the punch was thrown, yeah, probably about 47 seconds. That wasn't really the question I wanted to ask though, but you answered it and that was good. When do you think the impact actually happened? Let's try that one. When do we think the impact actually happened?
Oh, that second tick mark there, 47.
Probably like around here-ish,
Yeah, ish.
right?
yeah,
Maybe
like right
here,
before
right?
the-
Definitely
before the
before the head accelerates all the way back, right? Yeah, right. So we use graphs all the time. They're really helpful in helping us visualize what our data is telling us, right? Something like this is really nice, right? You can get peak acceleration in G's if somebody's head's been punched, right? So what are some other things, right? Well, guess what? We can do graphical solutions for derivatives, right? We did analytical solutions, right, where we actually take the derivative. But if you look at a curve, right, you can figure it out, right? So if you're given the position versus time curve, the velocity versus time curve is just the slope of that curve at every point, right? We watched a video about this and we talked about it. So potentially, if you're given a data set and you have the curve to describe it, right, you could come up with the slope at every point, right? And you could draw that curve, right? And then, well, we could do that again for the velocity versus time curve and draw the slope for our acceleration curve, right? So if you're given a graph, you can certainly do this. Now, I mean, really, well, I guess I didn't put the other slides in. You can also do this in reverse, right? You can also do this in reverse. If you're talking about the area under a curve, right? The area, if you had an acceleration versus time curve and you found the area under that curve at every time point, right? Then you could draw the velocity and so on up, right? All right, there it is. I guess I just inserted the slide the wrong way, right? So given the area, given the curve A, the acceleration versus time curve, right? The change in velocity between time 1 and time 2 is equal to the area under the curve between those time points, right? So where is this prevalent? Like where would you use this, right? Well, what quantity does an accelerometer give you? If you were going to put an accelerometer on something, right? What does that give you? What does an accelerometer do, guys? Measures what? Measures what? It's kind of in the name. An accelerometer measures an accelerometer measures something. There's something in the chat. Something brewing.
Proper velocity.
So we've got someone
Would it be like the change in velocity?
Yes, otherwise known as,
Proper velocity? Or
yes, the acceleration. The acceleration measures the acceleration, right? An accelerometer measures acceleration. Your phone has one, measures that. But guess what? Sometimes having the acceleration is not appropriate. Right? I'd rather have the velocity. I'd rather have the position. How do I go from acceleration to position? I have to take the integral. Well, I don't feel like trying to create a curve for this, right? I don't feel like trying to figure out what my function is for this, right? So I'm just going to take my data and I'm going to find two data points and I'm going to figure out the area under the curve at that point. I'll estimate that and I'll call that my velocity, and then I can draw my velocity curve. And then I'll do that again. I'll find the area under this curve between two time points, right? And I can get my position, right? So you can take data that's in one form or another and change it like that. All right, so that's graphical solutions. How often are we going to use graphical solutions in this class? Probably never. Probably never. All right, but let's talk about something that's inherently more exciting then, right? Curvilinear motion, right? We're going to cover position, velocity, and acceleration on a curved path. So like this is something like a snowboarder or a train. They both undergo curvilinear motion. You can kind of see it here, right? You can kind of see it here, but I will highlight it. Right? This is, hold on, this is the path, right? They used, right? So it's not, he's not going into, don't want you guys to get nervous. He's not going to fly into the city, right? It's not, it's coming down here. There's more mountain. Or, you know, you can, like that has that curved path there, right? So it's fine. So we're talking about particles moving along a curved path, right? We're talking about particles moving along a curved path, right? And so here's the math part where, you know, your post-lunch coma is really going to take over, right? So we have to talk about vectors, right? But do we really have to talk about vectors? Yes, we have to talk about vectors. All of these things are vectors. Vectors are love, vectors are life, okay? The position vector of a particle at time t is defined by the vector between the origin and the position that's occupied by the particle, right? Okay, so here's my vector. We'll call this one R, right? I'm going to change the color so that it's not super confusing, right? So the red one is R, right? And the blue one is called R prime. What is R prime? Well, at some point in time, I have moved, particle P has moved from point P to P prime here, right? And so that vector that describes the position there, right? So what is this vector, delta S? Well, that's the change in position, right? That's the change in position that we have between P and P prime. That is how much we have moved between the two particles. Now notice it's not curved, right? So that's technically we're gonna call that delta S, and you might remember this from geometry. That's technically the arc length, but not really, right? All right, so we're talking about a particle that occupies position P at some time, and then at some time T plus delta T, we're now at P, okay? All right, and we can use this vector in between to discuss the relative position of these 2 points, right? Okay, so let's talk about the instantaneous velocity. I want to know the velocity at a specific time, right? We live in a right now culture, and I want to know the velocity now, right now, right? Immediately, at this point. How do I figure that out? Well, we talked about this already, right? That is just what? It's just the derivative of the position at a specific time, right? So, right, we just use dr dt, right? So here's r, the derivative of this vector gives me the position, or I'm sorry, the velocity. Great. Okay. What if I want the instantaneous speed, right? Well, that's just what I want you guys to think of that as the magnitude of the velocity vector, right? Velocity is pointed in a direction, right? It's positive, it's negative, right? It has some sense of direction to it. Speed is just the raw amount of velocity that we have. Right? Speed is just, all right, well, we're going 70 miles per hour, right? That's speed. If I'm going 70 miles per hour in reverse, that's a velocity because it has that direction associated with it, right? If I have to specify the direction, I've now made it a vector. Okay. All right, so that's position, right? So if we take the derivative of the position, we get the velocity, and that's the same for a vector as it is for a scalar, right? It's the same for a particle as it is for a vector, right? So if I have the velocity of a particle at some time t, and then it has a velocity that's v prime at some other time, t plus delta t, the acceleration is just the derivative of the velocity vector, right? So in general, the acceleration vector is not tangent to the particle path, right? And why do I have to mention that? Because you might think that it is, but it's not, okay? It doesn't have to be. There's nothing saying that it has to be. It can be in whatever direction it needs to be in to describe our system, okay? So it turns out that if we're using vectors, right, we take the position and we take the derivative, and that's the velocity, and we take the derivative again, and that's the acceleration. Okay, that's it, right? So we're just talking about this as vectors. Well, there's a specific thing that we can do with rectangular components of vectors, right? So I want you guys to take a look at this, right? So this is in 3 dimensions, and when things are in 3 dimensions, they are less easy to understand, right? So we're going to actually simplify this and talk about it in terms of a 2-dimensional problem, right? Just x and y. We're going to do just Cartesian coordinates, meaning your standard x and y coordinate system, right? If I had some vector, right, there in 2-dimensional space, right, we can see that I can break this down into an x component and a y component, right? Break that down into an x component and a y component. That's going to be the whole focus of what we're about to do with rectangular components, okay? And so this is the part where we're going to start. I fear that I might start to really glaze your eyes over, some of you at least. So if I have a position vector, right, remember we're going to call that R, right? R is my position vector. This is in 3 dimensions. I can define R as follows: xi plus yj plus zk, right? What the heck, Dr. D? This is what the heck? Okay. Let me try this. X is the distance that we have moved in the x direction. I is the unit vector. Okay, so we can define a vector, right? If we had this vector x, right? This would be equivalent to saying the magnitude of that vector times the unit vector. Well, what's a unit vector? A unit vector is a vector in the direction of our motion, right? In the direction of one of our components, but it has the size 1, right? And it's pointed in the positive direction. Okay, it's pointed in the positive direction. So in this case, right, if we're looking over here in this picture, right, and we wanted to break down this vector R, right, we would have in the I direction, we would have some x sub I, right? In the j direction, or the y direction, we're going to call it the j direction, we would have this vector, right? And in the k direction, or the z, along the z-axis, we would have this. So in 3 dimensions, right, we have 3 unit vectors. We have I, j, and k, each corresponding with the x, the y, and the z-axis respectively. Okay. So can I have a negative there? Yes, you can, right? You can, because X can be in the negative direction, right? If you're traveling in the negative direction, your unit vector is then negative, right? Okay. Is this okay so far, right? So I know that sometimes you guys may not have seen these as I, J, and K before, right? And I forget what Professor Tomford said you guys may have seen these as. But we're going to typically use I, J, K to talk about our X, Y, and Z direction unit vectors. Okay? And notice I might, so just as an aside, right, I might draw these as, instead of, I might put the hat over them, right? I hat, J hat, and K hat. That's how I annotate these. I talk about these as unit vectors. You know, you put a hat on them, and that's fine. If you guys don't do that, but you associate it with actually being a vector like they have done here with the arrow, that's fine too. Okay. Okay. So we've got this position vector, right? This position vector R. Oh, shoot. Okay. Now I want to find the velocity of this, right? I want to find the velocity of this thing. So I'm going to take the time derivative of R. And I take the time derivative of R, and that's going to give me, now the important thing about unit vectors is that they don't change. They are constants, okay? The I part is, right? So we'll end up with dx dt times I plus dy dt times j plus dz dt times k, which is just, now you guys will notice there's dots here, right? And the dot just means that there's a time, we took the time derivative. That's all that means, right? That's all that means. But we're left with the velocity in the x direction times I plus the velocity in the y times j hat plus the velocity in z times k hat. So really, if we take the time derivative of our position, it's just the combination of the velocity in any of our directions, right? We're just adding up those three velocity vectors. That's what we're doing. Okay. And if you thought, well, let's try that one more time to get the acceleration, then yeah, that's what we're going to do. Now in 3 dimensions, again, this becomes confounded a little bit, right? Because it's harder to draw, it's harder to see visually. And myself, I am a fairly visual person, right? So I want to be able to kind of to make sure I'm understanding where everything goes here, right? Okay. Does everybody have any questions about this? Are there any questions here? You guys doing okay? All right. I know it's not, no, this is the heavy math part of today's class, right? The good news is I'm not expecting you guys to have to derive any of this, right? I'm happy as long as we all understand this, and this, right? The only time that you would have to derive these, right? The only time that I've ever had to derive these expressions from scratch is when I was in graduate school, and they're like, here's your dynamics class. And the dynamics class, the guy comes in and he's like, he's a Belgian guy with a very thick accent, right? And it's basically like, here's the expression for position. Now derive the entire, right, derive the velocity and acceleration, and tell me how it applies to Newton's second law. That was like day one. So that was pretty hefty, but that's fine. Okay. So what about rectangular components, right? I told you we'd break this down into 2 dimensions, and we're going to, right now. So we're going to ignore 3D for a little bit. We'll come back to it. We will come back to it, but we're going to ignore this for a second, and we're going to focus just on 2-dimensional problems, right? So rectangular components are particularly effective when components when component accelerations can be integrated independently. For example, projectile motion. So the x direction and the y direction accelerations and the z direction acceleration can all be integrated independently here, as long as we have initial conditions, right? We set this up like this. Okay. Again, we're going to be focusing on 2D for a little while. We'll get to a couple 3D problems, right? And we'll talk about that when we get there. All right, so I integrate twice here, right? Because I started with acceleration, and hey, well, would you look at that? If I integrate this twice, I find out that the velocity in the x direction, which we said is v naught x of 0, or v x naught. The velocity of the y is the original velocity minus gravity times time, right? And in the z direction is 0. Interesting, right? Okay. Well, look, we started here with x double dot is 0 and z double dot is 0. Turns out that this is still 0. And it turns out that the initial velocity here is just equal to the total velocity, right? Because why? Because we found out it's not accelerating, right? We know that it's not accelerating, so that means the velocity has to be constant, okay? So if we integrate it again with our initial conditions, we see x is equal to the initial velocity in the x direction times time. Y is equal to the initial velocity in the y direction times the initial position. Now, that should be times time, not times y. Guys, that's a typo. This is a t. Minus 1/2 gt squared, right? Well, those equations look awfully familiar to me. Where have we seen those equations before, guys? Where have we seen those equations before? Because I feel like I've seen them today. I feel like I've seen them today. Where have we seen those before? That's gonna bug me, right? I figure that one out. Don't those just look like these equations? Aren't those our uniform? Those are just our uniform kinematic equations, right? Kinematic equations for uniform acceleration. That's all that we've derived here. So it turns out that projectile motion is a special case where we have 0 acceleration in the x direction. We assume 0. We have gravity as acceleration in the y direction, right? Awesome. Awesome. So we're left with this, right? So the motion in the horizontal direction is uniform. The motion in the vertical direction is uniformly accelerated, and there's no motion in the z direction, right? So the motion of a projectile can be replaced by 2 independent rectilinear motions, right? Instead of talking about this as a curve, we can talk about this as how much did the motion change in the x direction and how much did it change in the y direction, right? Because at every point, let's think about this like a graph, right? If this was an XY graph, right, measuring position, every single point along this line has an XY coordinate, right? So if we want to know the position at any time, right, because each one of these points happens in time, but it also has an XY coordinate, right? So I can use the conjunction of these equations to figure out how much time it takes for something to happen, and then where it was either in the X or Y direction based off of when it happened. Okay. Projectile motion is likely not a new concept for you guys, right? Taking physics 1, this should have been covered in physics 1. I don't think that I've I'm not going to sit here and say, well, I invented projectile motion. I didn't. I didn't. I just really, I like how this all ties things together. It's really nice, right? So let us try this one. Okay. So much like our other problems, right? I'm going to try this one first today. You guys aren't going to be on the hook for really very many. Next class, now that we've laid the groundwork, you guys are going to be doing most of the legwork with the problems. Okay. So let's talk about this one together. Right? What do I have here? What you know, as many people are wont to do, right? We're going to fire a projectile from the edge of a cliff, right? Because seems like a good idea. Why not? Right. So I'm going to fire a projectile off of a 150-meter cliff with an initial velocity of 180 meters per second at an angle of 30 degrees. If I neglect air resistance, I'm going to find first the horizontal distance from the gun where the projectile strikes the ground, and B, the greatest elevation above the ground that the projectile reaches. Okay. Okay. So where are we going? Right. So I've got my picture already, right? Because step one should always be to draw a picture. And with some of these kinematic equations, it's not that big of a deal. But you can see, right, I've got my initial velocity from my point. I'm going to draw a dashed line for my trajectory, estimated trajectory. I want to find what, right? Well, let's write down the things that we want to find, right? So for part A, I want to find x, which is the distance to where the projectile lands, right, as shown on my diagram here. And for part B, I want to find y, which I've designated there, right? I want to know the total, the highest point above the ground, right? The highest point above the ground that this travels. That's what I want to know. Remember, we can use our constant acceleration equations here, but we are going to have to do a little bit of trig, right? So none of those crazy trig identities, mind you, right? But we are going to have to break down this velocity into an x component and a y component, right? Because right now it doesn't really help us. We want to analyze this as an x component and a y component, right? So let's draw that on here. Let's call this v sub x. We'll call that v sub y. Because, you know, creative names, right? Creative naming conventions. Great. So v sub x and v sub y. Now, the thing about vectors, right, is that I can actually say that this is also v sub y, right? It's not that there's two vectors, it's just for the purpose of creating the right triangle, right? Because I can slide this vector anywhere that I want along this x vector, and it's okay, it's fine. But for the purpose of figuring out what v sub y is, it's sometimes easier to draw it as the vertical leg of this triangle, right? I mean, it's the same as doing this in here, where this is your 30 degrees up here, right? Because trigonometry. But just keep that in mind. I will erase this one so we don't all get super confused when you go back and. So anybody watching this on YouTube isn't like, why is there so many vectors there? Okay. All right, so it's pretty clear what we want here. We want the x distance that it travels and the y. We can break this down into components. And the first thing I'm going to do is actually break down my velocity into the components, right? So let's talk about that, right? So here's my velocity triangle, right? Here's my velocity. Here's v sub x, and here's v sub y. Now remember, You can always go from, if you're given two component velocities, you can always get the resultant, right? What is the resultant? Well, it's technically the total, right? It's the resultant. The resultant's the total. How do I get that v sub r? Remember, Pythagorean theorem tells me that a squared plus b squared is equal to c squared, right? That's, in this case, translates to vx squared plus vy squared is equal to v. I've called it VR for resultant. Is that going to come into play here? No, but that's a little bit of a trig review, right? And this is a helpful expression if you're ever given, a velocities in a components and you're asked to find the total velocity or the resultant velocity, right? This is an important idea of using Pythagorean theorem. All right, so I want to find v sub x. How do I do that, right? Well, we got to use trig, right? And so for this particular, for this one in particular, well, what is that? Well, that's v naught. Let's see. All right. SOHCAHTOA, right? Sine is opposite over hypotenuse, so that's not that one. Cosine is adjacent, right? So that's the one, right? So we're going to say that's going to be cosine of 30 degrees, right? Because Vx is adjacent to my angle. The y component is actually going to be the sine of 30 degrees, right? Now you'll notice a lot of things in the textbook. They like to use 30 degrees a lot, right? Because that's a 30, 60, 90 triangle, which has special significance, right? What is the special significance here? Well, the sine of 30 degrees is 1/2, right? Sine of 30 degrees is 1/2, which is nice, right? All right, so everybody's cool with how I got my components, right? That's not, hopefully not a mysterious thing, right? We all love right triangles. Right triangles is, like, I don't mean to be biased, but I'm gonna say it anyway. Right triangles are the best triangles. I mean, I think that is a fact. I don't think that's an opinion. So you guys can fight me about it, right? I know I've angered 50% of the internet by saying that out loud, but right triangles are the best triangles. Right? They're the best triangles. All right, so let's plug some things in. Cosine of 30 degrees equals 180 sine of 30 degrees, right? And I'll just write it down here, right? When we crunch everything, Vx becomes 155.8 meters per second, and Vy is just 90 meters per second. Okay. Now remember, we know a couple of things beyond this, right? But we were asked in part A to find the distance that we need to travel, that we travel when we hit the ground, right? So so we've actually been given a little bit more information than we think we have, right? We have been. What is the position, the vertical position when we hit the ground? What is that vertical distance? Do we know that vertical distance when we hit the ground? If we start at the blue dot, right? If we're starting here, what is this vertical distance from here to the ground? Right, we'll call it h, just so we don't get confused here. What is this height? How far have I traveled if I'm at the ground, if I'm here? Come on, guys. Somebody.
150.
Yeah, it's 150. We moved 150 meters. Why is that important? Well, we need to figure out how long it takes us to get here, right? Because if we look at our equations, right? If you go back one slide, we look at these equations. For my x position, I know v x naught, but I don't know the time, right? This is how I'm going to find that x position. So I need to figure out what the time is. How do I figure out the time? Well, there's another event that happens at that time, right? And that is when y is negative 150 meters, right? It's below the point that we started. We know this. We know everything except for the time in this equation. So we can figure out how long it takes for us to travel that y distance, because that's going to be the same amount of time that it takes us to travel the x distance. Does that make sense? We know that at that time, we have to be at that xy coordinate, right? We know that. So we can use the y direction to figure out the time, and we can use that time to figure out our x position. Okay. So let's go to this slide. So the first thing we're going to do, right? The very first thing is we're going to find the time it takes for the projectile to hit the ground, which means that y is equal to negative 150 meters. Doing that, we can use the equation from the previous slide. This is y is equal to v naught y times time plus 1/2 a t squared, right? Now, it's really minus 1/2 9.81 times time squared, right? Because the acceleration is negative 9.81 meters per second squared. So I'll plug in some numbers here, and we'll have that negative 150 is equal to 90 times t minus 1/2 9.81 t squared, right? And so we'll solve this. We will solve this for t. It's a quadratic. We can use the quadratic formula, and we'll get these two terms. Which one of these should I choose? Which one of these should I choose?
Probably the positive.
Positive, right? Because as we went over again at the beginning of class, none of us are time lords, or are we? I thought we proved it last class. Remember, we did our test, and nobody came back to let us know that they're time travelers.
Anyone could forget.
It's true. Let's try it again. 2:25 p.m. on 9/16/2020. Room 1345 in the engineering building. Oh, by the way, we've changed classrooms. We're gonna be in 1345 when you guys get back to campus. Okay. It's a better room, in my opinion. It also lets me write on the board, or the smart podium, which is nice. Nobody again. Either we're all really bad at remembering, or we just don't travel through time, or you know, by being a time traveler, you have signed papers saying that you wouldn't let people know, right? That could be it too. If I was a time traveler, would I travel back in time and let myself know? I don't think I think that's against the rules, right? And they put you in time traveler prison, right? Which I've now wasted enough time talking about. Okay, cool. So we've got our time here, right? So now that we know how long it takes, we can figure out how far we go in that amount of time, right? What is our lateral distance? And based off of the previous slide, we know that our equation looks like this, right? So I can plug in my values, and I would get x is equal to v naught x was what we calculated, was 155.88 times 19.89. And so we find that in about 20 seconds, we end up traveling 3,100.45 meters. So 3,100.45 meters. So pretty decent. That's part A, right? That's what we needed. We needed that x distance. So how now do we find part B? We want to find y. What do you guys think? What do you guys think? Let's go back to the equations again. So we can have those up there, because that would be fun. What do you guys think? If I wanted to find the y distance when the position is, all right, so what am I looking for? I'm trying to find y, I'm trying to find the maximum height. So right, I need to find the maximum height. How do you guys think we should find the maximum height? How do you guys think we should find the maximum?
You have to do something with like acceleration and find the point at which the velocity that the velocity becomes 0.
So yeah, Zach, you're on the right track, right? What does it mean if we're at maximum, right? So the shape of our trajectory is basically a parabola, right? It's basically that, right? And so at maximum height, we are at the peak. We talked a little bit about this in class when we were talking about derivatives, right? If we're at the maximum, what does that mean our derivative is? What does that mean our derivative is? We're at the maximum point. What does that mean our derivative is? If you were to zoom in really close on that, what would it look like? How would it be changing?
Be like a horizontal line almost.
Right, it would be a flat line, right? Which would mean that the slope of that line is
0.
0, yes. So when we have a local maximum, we have a 0 derivative, right? So if the position is a maximum position, the derivative of position is velocity. So our velocity is 0 at maximum height, right? Think of it this way. Another way of thinking about it. If you have a projectile, right, that's going up, right? We're flying, it's going up, 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 up. Now it needs to change direction because it's at maximum height, right? Before it starts going down. So the velocity, it's going to actually slow down, right, until it hits maximum where it's 0, and then it's going to speed up again, right? Because it has to change direction at that point. There we are. All right, so which ones are we going to use here? Well, we're going to start using this equation, right? Vy, because I know everything except the time it takes. And then we're going to plug that back in to our y equation once we get the time, right? So again, these questions, these problems, oh no. Yep, that happened. Oh well. If I move too fast, it does the trick where it pulls all of the slides like into one slide. Oh, there we go. All right. So first thing we have to do, we have to use this. Vy is equal to v naught y plus acceleration times time. Right, as we just said, we know that Vy, right, we're going to say that's 0 because we're at maximum height. So we're expecting that to be 0. This is going to be 90, right, because we calculated it. Minus 9.81 times time. I solved for time. I solved for time. That's 9.17 seconds. .17 seconds. Okay. So where do we go from there, right? Well, we're gonna go back to that y direction equation again, right? So y is equal to v naught y times time plus 1/2 at squared. But this time, we're trying to solve for y. So y is equal to 90 times 9.17 minus 1/2, 9.81 times 9.17 squared. So when we solve for that, y is equal to 412.84 meters. We're all done, right? We did what it said to do. Yeah. Yeah. Everybody's okay with that result? Nobody's got any issues with it? We need to know how far off the ground we are, right? That's what we wanted to know. Did I actually find how far off the ground we are?
Wait, is that the I was just thinking about this just now. Is that the height above the cliff or above the ground?
Yes, Zach, that is the height above the cliff. That is not the height from the ground. That's the height from our starting point. So how do we figure out how far above the ground we are? Well, we started 150 meters above the ground, so we add 150 to it. All right. So y, let's call this y sub ground, is equal to 150 plus y, which gives me 562.84 meters. Right. That's it. So bottom line, right? These problems, you need to think about it, right? You need to figure out, typically the way that these in general break down, right? You figure out how long it takes for something to happen, right? Then you plug that time in to get the other coordinate that happened, right? So you know where a y coordinate, you find out where an x or a y coordinate happens in time. Then you use that time to find the other x or y coordinate, right? That's basically the name of the game, is find the time it takes for something to happen. That's the same amount of time it took for something else to happen, right? Evaluate what the other direction was. Right. Is there any questions on this? Again, I don't think that this is like brand new for anybody, right? You guys took 121, I'm sure that Doc McCarthy or whoever you had, right, covered this. Okay, we good? We good? Yeah. Well, in that case, let's find out. So that problem, the problem we just did, right? If you fire the projectile from 150 meters above the ground, what launch angle gives you the greatest horizontal distance x, right? Now in the chat, leave your answer. Right? Is it A, 45 degrees, B, less than 45 degrees, C, greater than 45 degrees, D, it depends on the launch velocity. So is it A, B, C, or D? What is going to give you the greatest horizontal difference? We got a lot of A's, 45 degrees. Well, it's actually less than 45 degrees. It is. And For next class, for participation, before next class, post in LoudCloud as a private message to me, a private form to me, a picture of you proving it. You can use real numbers. You can crunch the numbers and figure it out.
Can you show the problem one more time so I can just get a photo of it real fast so I could send it to you later?
Absolutely not. No, I can do this. You know how hard it is for me to scroll back up through these slides? I mean, this is a bit ridiculous. It's a joke, by the way. It's hard to tell if people, I once had a student say, like, because I will say things like, guys, I don't know what I'm doing. I never done this before, right? Which is obviously supposed to be a joke, right? Because I'm the professor and we hope that I've done these things before. But I had a student once comment that he often claims that he doesn't know what he's doing. So I always have to be careful with some of my jokes, I guess.
So are we just doing the problem, or are we proving that the angle needs to be less than 45 for the
Prove that the maximum, you just need to prove that the maximum happens at less than 45. Mm. And we'll talk about why next class. But for right now, that's really all I got for today. We were going to do that activity, but we didn't. So that freed up about 20 minutes. So yeah, we're done for today. You guys get 20 minutes early. All right. That's not the thing. What's happening?
Do we just submit it in a private form for participation, or is there like a assignment thing to do it in?
You can just, there's no assignment Dropbox, okay? There's no assignment Dropbox, so just post it in the private forum, or you can email it to me. That's fine, either way. I'm gonna put this up. Hopefully you guys can see the poll everywhere. All right. Then you're done, then you can go. We're good for today. I've got office hours at 3. If you need help with anything, I would urge you to, if you haven't looked at the homework yet, to start looking at the homework today. I think it'll help you. And I'll see you guys on Thursday, and we will do, I promise, I guarantee. I'm going to hype this really well. Right? I guarantee that you will have fun on Thursday. I guarantee it. Guarantee it. Or I don't really have anything I can give you in return, right? But it's a fun back guarantee. If you don't have fun, I guarantee you that you will get your fun back. I don't even know what that means. It doesn't even mean anything.
I don't know what it means, but it sounds like a great deal.
All right, cool. I promise it'll be a lot of fun. It would have been more fun if you guys were in class to do the activity, but I still think we'll have a really good time. So we'll just keep that in mind. Right. So yeah. Once you post, you're good to go. And I'll see you guys on Thursday. Or Friday, rather, not Thursday. Thursday will be tomorrow.
Have a good day, Professor.
Take it easy.
See you later, Professor.
Bye.
Take it easy.
How's it going?
See you.